Okay, so thank you very much for the introduction. We celebrated 100 years of quantum mechanics, of course. In physics, we're always looking for unification, which is the main purpose of physics. We have been unifying different issues since the beginning. One solid example is quantum field theory, which I will mention later, many others, which I will be mentioning during the talk. It's an introductory talk, suitable for students, basically, and I will mention a few open problems, which is always important to mention. So I am a professor, assistant professor from University of San Joseph in Macau. My PhD from the University of Osaka. They changed the name recently, so it's called the University of Osaka. In 2014, my supervisors were Yutaka Hosotani and Hideo Kodama. My master in science physics was in Colombia, Universidad de los Andes, 2008, and my bachelor is mechanical engineering, Universidad del Norte, 2004 in Colombia also. So, I mean, many questions. The first question which comes to the mind to anyone is, why do we need quantum mechanics? And everything started in 1900 with Max Planck, who realized that the only way to explain the black body spectrum, which is this one followed here, intensity versus wavelength, was assuming that the radiation comes in discrete packets. Subsequently, Einstein used that hypothesis for solving the photoelectric effect, as we will see in a moment. But for the moment, pay attention that this is what the classical theory would say, and this is what was observed. So Max Planck, applying arguments of statistical mechanics, which is a course in physics actually, he realized that the only way to solve this is assuming discrete packets. We call it today photons. So, and guess what? I mean, Hawking in the 70s, he realized that the black holes emit radiation in the same way as a black body do. This is the spectrum of black body radiation. Well, this is for fermions and bosons actually. But the point is that it's nice to see that this phenomenon is generic. It happens not only in ordinary black bodies, but also in black holes. So what Einstein took the hypothesis of Max Planck, and he, with that hypothesis, assuming that the light, which is part of the electromagnetic spectrum, come in discrete packages called photons. He called it photons, and then he could explain one phenomenon which wasn't solved by the time, which was the photoelectric effect. The idea is that when light collides the materials, the electrons move such that they produce electricity. Basically, this is the principle of photocells, photovoltaic cells. So it was not well understood by the time. In 1905, Einstein wrote a seminal paper about it. Classically, you would expect that even if the frequency of the radiation is low enough, is low, and you wait a long time, you would expect the electrons to move, but that didn't happen. So classical theory failed at this point, and is where quantum mechanics entered. So the key points of the photoelectric effect were the following. There was a minimal energy after which an electron can really move. So it means the photons, they need to have a minimal frequency such that they have enough energy for making the electrons to move. So it doesn't matter the intensity, what matters is the frequency. The intensity doesn't affect the kinetic energy of the electrons. Intensity only affects the numbers of photons coming, incidence over the material. And the kinetic energy is affected by the frequency because, as you know, the energy of a photon is proportional to the frequency. For those who have studied physics, for those who have not studied physics, now you know. This is the energy of a photon, the Planck constant times the frequency. The kinetic energy of the electron release will be that energy of the photon minus the energy of the bond, the energy bonded, which bonds the electron to the material. So it's pure conservation of energy, this formula. So after came, of course, this was not the development of quantum mechanics, was the early stage. Then other principles came, like the Heisenberg certainty principle, which is one of the pillars of quantum mechanics. And it suggests that we cannot define position and momentum simultaneously. This means, for example, let's assume a particle is moving somewhere, or I put a particle in a room and I don't know where the particle is located. That particle has a well-defined momentum, but I don't know its position. But once I try to look into its position, I have to apply light, and that light has to collide that particle. I destroy its momentum, but already I know its position. So there is a duality between these two variables, position and momentum. It means I know one or the other. I cannot know both simultaneously. That's quite important. And of course, this comes the famous Schrödinger cat, whether the cat is alive or dead, where the response is both. When we prepare a quantum state, it's a superposition of possibilities. We don't know at the end what will be the output. And all what we know is that there are certain probabilities of certain outputs. For different experiments, will give you different answers. So the Heisenberg uncertainty principle is a special case of a more general principle in quantum mechanics. It's called wave-particle duality and complementarity. So it means that there are always pairs of complementary variables. Position and momentum, they are complementary to each other. I know one or the other. The angle and angular momentum are also complementary to each other. I know one or the other. Energy time is also, they have their own uncertainty principle. So in quantum mechanics, I can define very well certain set of variables, and there are other sets of variables which I will never know. So I have to define which set of, or I can know partially both. For example, I can create a wave package like this, where I know partially the position of the particle because there are some possibilities here. Here, sorry, and I can know partially the momentum of the particle. So these compromises have done through the wave package in quantum mechanics. So let's go to some of the development of quantum mechanics. The starting point, as we mentioned, was Max Planck, Einstein. Then after, we can mention a little bit about Louis de Broglie, who realized that all the particles have an associated wavelength. For example, even the electrons or, or any object has an associated wavelength, which is proportional to the, is equal to the Planck constant divided the momentum. So the idea of this, let's assume that we calculate the Broglie wavelength for the electrons. If the wavelength is longer than the separation of two slits in a double slit experiment, then a question is whether the electron cross the left or the right hand side slit. And guess what? The response is that it crosses both slits simultaneously because the electron behaves as a wave, which is able to be everywhere in a space here. So at the moment of crossing this double slit and finding this barrier, the electron will decide to cross simultaneously the left and right-handed slit. This is the Copenhagen interpretation of quantum mechanics, and this creates patterns consistent with the interference of wave functions. So it's like we can create a wave function for the electron, the motion of the electron. We have a probability associated to that wave function, and we can calculate exactly the interference patterns here and where will be located the points of brightness over all the points of collisions for the electron. So, but the Bai was not happy with the fact that de Broglie formulated a wavelength and there was not a question for the wave. I mean, there was no way of equation associated to quantum mechanics. So he discussed with Schrödinger and suggested him to develop an equation. And then it came out that Schrödinger copied more or less the formulation of Hamilton, and he mapped it to quantum mechanics, doing then the Hamiltonian formulation for quantum mechanics, as you see below here. This is the Schrödinger equation. The left-hand side is the time-dependent part. This is the Hamiltonian of a free particle. Well, a free particle is the zero. Depending on the potential, the particles will behave different. But the point is that the particle is represented through a wave function, which reflects the amplitude of probability for finding that particle somewhere. So for example, if I put a ball inside a box and somebody asks me where is located this ball or this particle, which is very small in principle, so I would say I don't know, but I know it's inside this box. I know it's constrained by Lx, Lc, Ly, but I don't know exactly where it is. And if I try to look into its exact location, then what will happen? I will destroy its momentum. So this is an example also of the uncertainty principle, about the complementary principle, and about the fact that quantum mechanics is a probabilistic theory. It tells us what is the probability of finding a particle somewhere. And actually, the probability is calculated for the square of the amplitude of the momentum. So talking a little bit about the uncertainty principle gives us vacuum energy. When we quantize the harmonic oscillator, for example, we obtain this spectrum. Of course, the ground state of the harmonic oscillator is this, and it has this energy, 1/2 h bar omega. And guess what? We believe that since we copy in quantum field theory the algebra of the quantum harmonic oscillator, we obtain also a ground state energy, and we believe, uh, many people believe, that this is the energy which accelerates the universe, which expands the universe. It's called vacuum energy. And it's a consequence of nothing else than the energy time uncertainty principle. And this is more a clear image of the spectrum of the quantum harmonic oscillator. So, and there is a reason why the ground state has energy. The reason is simple. For example, if I put a particle in the bottom of the potential and that particle doesn't move, for example, I could know its location and position and momentum simultaneously, violating the uncertainty principle. So it's because of the uncertainty principle that the quantum harmonic oscillator has a ground state energy. Quantum mechanics includes energy. It's not a secret that when we throw a photon or a radiation to an atom, the electrons get excited, and vice versa. When the electrons decay in energy levels, they emit radiation, consistent with the separation of the energy levels. This is one of the most powerful predictions and applications of quantum mechanics, the laser, for example, which is a technology we use. Now, after the evolution that Schrödinger did the equation, etc., that's what we call single particle approach. Single particle approach is non-relativistic. Now, the challenge was to unify quantum mechanics with special relativity. This is done through quantum field theory, but this was a slow process. And the reason is, while classical physics doesn't constrain the causality, in special relativity, we have a causality count which constrain which events can be communicated with each other. So the single particle approach in quantum mechanics for the relativistic approach, it failed in a very miserable way. And the reason is because we cannot interpret the wave function as the probability of finding a particle anymore when special relativity is included. And the reason for that came from the Klein-Gordon equation. Look at the Schrödinger equation. It's first derivative in time, second derivative in space. It's non-relativistic, clearly, because it has no symmetry between space and time. But look at the Klein-Gordon equation. It has symmetry in space-time, second derivative in time, second derivative in space. But it has positive and negative energy spectrum, so it was an unstable equation as a single particle. Nowadays, we know that as a quantum field equation is correct, but it has to be a multi-particle approach. Interpreting the wave function, instead of interpreting this solution as a wave function, we interpret it as a quantum field nowadays. So, and the reason why this evolution was necessary was due to Dirac. Dirac realized that the failure of the Schrödinger as well as the Klein-Gordon equation is in the order of the derivatives. The Klein-Gordon equation is second derivative in time, second derivative in space. So Dirac proposed himself to construct an equation, first derivative in time, first derivative in space. With his algebras, he could predict the existence of the positron. It means the positron was predicted theoretically in a paper, in a piece of paper, before its detection. Subsequently, we realized that not only the positron, but every particle has an antiparticle. And when particle and antiparticle meet, they annihilate and they emit radiation. So one question is why the universe is full of matter and not antimatter if it was supposed to be symmetric at the beginning. I think the responses are appearing now in the Large Hadron Collider, in my understanding. Now then, of course, after Dirac came the development of quantum field theory, which is a multi-particle approach. It means the vacuum is rich. The vacuum generate particles, create particles, destroy particles permanently, and we can collide two particles and generate other particles, and vice versa. Some particles can be annihilated, disappear completely, and emit radiation. So there are many processes in quantum field theory. It's quite complex for enumerating here, but the Klein-Gordon equation as well as the Dirac equation are both correct if they are interpreted as a quantum field equations in quantum field theory. And they both respect microcausality. This means that quantum mechanically, one particle can travel faster than light technically, but when that happens and another other part antiparticle appears, annihilating the particle. So it means that it's not possible to travel faster than light, even in quantum field theory, when we pose special relativity. So the developments of quantum mechanics continue. Quantum field theory, we have tried to unify general relativity on quantum field theory unsuccessfully. This is an open problem. So there is no way to quantize gravity. We have a string theory, we have loop quantum gravity, we have candidates for quantum gravity, but nobody can claim that they are seriously the theory of quantum gravity by the time. But still, how can you use quantum arguments for predict the evaporation of black holes? For example, the black holes not only absorb particles, they also emit particles. And Hawking used a semi-classical approach, which is using a standard general relativity and using arguments of quantum field theory in curved space-time for deriving this effect. And what he did basically is to compare two vacuums, one before the formation of the black hole, one after the formation of the black hole. And when these two guys start to discuss which particles you see, these guys say that I see particles, and this guy say I don't see particles. And this can be seen from the Penrose diagrams. Well, now let's close this talk with applications of quantum mechanics. You saw more or less the concept issues, how the quantum mechanics was developed, how it became quantum field theory. But recently, quantum technologies appear. The governments are investing a huge amount of money, and we have quantum computing, which will allow us to store information in qubits instead of ordinary bits. Normally, ordinary computers store information in zeros and one. In quantum mechanics or quantum computers will allow us to store information in linear combinations of zeros and one. And if you make the product of this qubit with another, the number of possibilities for storing information is almost infinite. So it means quantum computers are not only faster, but also they store much more information. Also, we have quantum communication. People are trying to stabilize and generate quantum states and creating communication channels such that we can use quantum principles. There are several challenges. Some of them are technological because keeping stable the quantum system without collapse is a challenge. Keeping a stable entangled system is a challenge, and many other possible noises which might affect the evolution of a quantum system. Now, for closing the talk, I will talk about some open problems where still quantum mechanics is there. The dark energy as a vacuum energy. Is this correct? Well, this is still an open problem. There are several researchers, including myself, working in this. Superconductivity at high temperature. We know that superconductivity is a macroscopic manifestation of quantum mechanics because are the quantum principles which generate this phenomenon, and it can be observed, and we use actually in our current technology the maglev or the trains which travel super fast. They levitate, some of them levitate, and they use the superconductivity principles in the lines. And the neutrino mass problem, neutrino oscillation is a quantum phenomenon, for example. Still, nobody understands the mechanism of neutrino mass. So it's a research which are also doing currently. The black hole information paradox. What happens when the information, when enter a black hole, the black hole emits radiation, but that radiation doesn't bring information back. It's thermal. So what happens with information? This is a violation of unitarity, something which challenge quantum mechanics because quantum mechanics says that information doesn't disappear because that's why we use unitary operators which help us to preserve information. And this is called unitarity. In conclusions, for closing, because the time is almost over, quantum mechanics has several applications in not only theoretically speaking, but also practically. Quantum mechanics emerged as a necessity for explaining observations that classical physics couldn't do. Relativistic quantum mechanics as a single particle approach fails, bringing out certain problems. The core theory of relativistic quantum mechanics is quantum field theory, and we use every day accelerators. We use every day for unifying theories. The electroweak theory, for example, was formulated by using the formulation of quantum field theory. I didn't mention spontaneous symmetry breaking or these things because I think it's quite complex and there is not enough time for covering that. In physics, we have a permanent pursuit of unifications. Quantum field theory itself is a unification of quantum mechanics and special relativity. So thank you very much for this opportunity.
Thank you. Thank you for your interesting talk. I will now invite our second speaker, Dr.